There we go. Alrighty. Where did we leave off last time? We did non-standard conditions. We're talking about batteries. Okay, that's right. That's right. All right. So, for to continue, I think we did not talk about lithium batteries yet. These are going to be super useful batteries. We use them all the time. Our cell phones have them. Many of our kind of high energy use electronics that we like to carry about use lithium batteries, laptops. Um, they're super useful for two reasons. First off, is it's an extremely light metal, right? It's the lightest metal. It's only got three protons, right? So it's very small. Its mass is very small compared to other, like the lead acid battery, for example. Lead atoms are much heavier, much more dense than lithium atoms are. Lithium will actually float on water. It's so light that it will do that. It's not dense at all. So as a result, we can have a lot of it and it won't weigh very much at all. So we can have a large amount of lithium there without it causing something to be very heavy. So we can have a lot of kind of energy density there. We also know that the potentials that are associated with lithium are very high. So we saw that with the batteries that we looked at the lead batteries and we looked at the nickel cadmium batteries. These ones had voltages of 1 to 1.5 volts, something like that, right? Lithium batteries typically have voltages of 3.7 or so per cell. So we're seeing that we can have really awesome kind of the ideal combination of things here. So we can put a lot of lithium in because it's super light. It's not going to weigh us down. And it also has a very high potential. So we can get a lot of electricity out of it. So we kind of have two things working for us here. We can pack a lot of lithium in, and each lithium gives a lot of electricity, so we can kind of really work with that lithium. So how do these work? Typically you'll have no O2. You'll have a cobalt based uh, electrode and you'll have graphite as your other electrode. You have kind of this area in the middle that is permeable. Lithium kind of will just migrate back and forth as the battery is charged or discharged. What's interesting about this is that the cobalt, when it is, the cobalt is actually going to be doing the chemistry here. So cobalt 3 plus to cobalt 2 plus is the chemistry that's happening here as things are happening. Cobalt, oops, I put it on the wrong side. Need the reduction. If we go ahead and look up cobalt's charge, or not charge, potential. Let me pop that open real quick. Let's go ahead and find it. This reaction has a pretty high potential, right? It happens. I just saw it. Where did it go? Cobalt, no, where did you go? Is a potential of 1.82, right? Just for this half reaction. So very kind of very nice reduction reaction happening here. So as the electrons are going to be going into the cobalt, the lithium is going to be migrating in towards the cobalt side of the cell here. If this is the reaction that's going to be taking place, this is the reduction side. The reduction is the cathode. And you'll have your graphite anode here on the other side. And so you can move your lithium around as you go through it. If you remember lithium, as it moves around, lithium has a reduction potential of negative 3.04. So decoupling these two reactions is very, very energy producing. You see that this adds up to 4.8 or whatever, but we're going to see that in reality, you know, when you actually add these things up, yes, you get 4.8 in theory, but there's things called overpotential, like resistance to the circuit and concentration effects that always kind of reduce the like theoretical voltage that you can put out. So you have your theoretical voltage, your real voltage outside of this is going to be about 3.7 or so. So you are going to get a little bit of some disconnect there. So you will lose a little bit just from resistance and all that sort of thing. So we're going to see that these potentials put together make very good batteries. We use graphite and then the cobalt 3 plus here as our kind of very nice cathode. We have our graphite anode. The lithium is going to move over there and accept electrons. Or rather, the electrons are going to be coming from there, from the lithium, and it'll become lithium plus, and the lithium plus will move over to help balance out things as the electrons are moving around. So, exciting stuff. So, that's how lithium batteries work. Again, the idea here is that you have nice compact energy density. You have a lot of energy that can come out from a relatively low mass, so a very good kind of combination there. The last kind of battery, even though it's not a real battery, is fuel cells, which of course use the reaction of hydrogen plus oxygen turning into, actually let's do it this way. Right, you probably have heard about hydrogen fuel cell cars. They are ideal, right? You use hydrogen as a source, you produce water. There's no carbon that's associated with this process, so you can not have any carbon entering the atmosphere. We just have water that comes out. Water, as we know, is already abundant in the atmosphere. It'll just come out down as rain, and poof, we have not put in any carbon to the atmosphere. If we look at the actual reactions that are happening with this, we have oxygen plus, I don't want to remember these, 4 hydrogens plus 4 electrons, turning into 2 waters. And then we have, I'm sorry, this is not the right equation. Or maybe it is. Yeah, it is. And then we have the hydrogen, of course. Yeah, duh. We turn this into the 4H plus and the 4 electrons rather. This, of course, is 0 volts. We have our standard hydrogen electrode here, and then the one for the oxygen reduction. Let's look it up. Oxygen reduction. Why did I choose oxygen? Okay, there it is. Nope, that's the other one. This table's too damn big, you know. Okay, let's see. No, not that one. That's a radical. Aha, plus 1.229. No, that's right. Okay, so we do get some nice voltage out here. Again, we're looking at voltages of around 1 volt. Obviously not enough to really do a lot, but we throw in more and more of these. We can just stack them all right next to each other. make as many volts as we want, that's going to increase the size. These typically operate at around 80 Celsius or so, which is a huge difference from the, some, what do regular car engines operate, like 2000 Celsius or something? So much, much cooler temperatures involved here. However, this does tend to make the reactions pretty slow. Even though this is a combustion type reaction, it is pretty slow at these temperatures. And so you use catalysts. I think platinum is kind of the main one here that we use to speed it up. And the reason that hydrogen fuel cell cars are so expensive is because of this catalyst. So the platinum there is expensive. That's what causes the high cost. If you want to buy a Mirai or what's the Honda and Clarity, those are going to be in the $50,000 range because of this platinum that's used in these fuel cells. Other than that, like things are very nice with them. You can go buy hydrogen at the gas station instead. It is a little bit dangerous though, so there is research going into not only looking at cheaper catalysts but alternative sources of hydrogen for this instead of H2 gas, because H2 gas, as you know, is pretty explosive. Hindenburg, go back to the Hindenburg when that blew up. So those are kind of areas of research where people are trying to make things a little bit more affordable for everyone. So I don't know if you know, but like Toyota and Honda and the ones that have the fuel cell cars, the fuel cell engines, they do usually offer, because they're so expensive and they're still working on making them cheaper, they do typically offer like free fuel for like 3 years or whatever. So at least they kind of offset it a little bit, but obviously those are pretty expensive still when you can get like a Tesla Model 3 for a lot less, right? So anyways, we don't need to talk about cars right here. So, but just another common up and coming, shall we say, not battery, but kind of galvanic cell that we want to look at. And that electricity, of course, is used to turn the motor, which will do all sorts of other activities in your car. So, fun stuff. So, those are kind of the more common batteries. So we have the lead acid battery that's used to start your car. We have the alkaline batteries, which typically use nickel or cadmium or both. We have the lithium ion batteries, which are super energy efficient, or density efficient rather. And then we have these hydrogen fuel cells. These are kind of the more common batteries that we'll talk about in chemistry. Alrighty, so enough about batteries. We have two kind of more sections here. The next one is on corrosion, which is kind of unwanted spontaneous electron transfer reactions. Spontaneous, nope, forgot a T. Spontaneous redox reactions. Of course, the most notorious and probably most expensive for the world is rusting. It's a huge problem, right? When iron rusts, it loses a lot of its good properties. It becomes very brittle. It flakes off, and it's kind of useless. And unfortunately, this reaction is spontaneous, and it happens in the presence of water in either acidic or basic conditions. And so we're going to see that we have a couple of reactions happening here. So we have the same one that we just looked at. Oh, sorry, this is going to make, is it 2 waters? Yeah, 2 waters. And we saw that was what, 1.229 volts. And the other one that we're going to have is iron oxidizing to, first it's Fe2 plus, I think, and then it goes to Fe3 plus later. Yes, it does. It does. So slightly basic conditions will still go for it, but if you go super basic, yeah, you'll stop the reaction from happening. So it is more favorable to have it in acidic conditions for sure, but it will still happen a little bit in slightly basic conditions. If we look up this potential, oh my goodness, okay, iron at least we can look up easily. That one's not got subscripts here. So let's look up irons. We're going to see we have multiple kind of stages of iron. Come on, where is plain old 2, 2, or 0 to 2? Aha. So, although this is an oxidation potential, I guess I should have written it as a reduction, but the reduction is a negative value, so this will be plus 0.44 volts, if you put it this way. And then we do have the one more step where it will be oxidized from iron 2 plus to iron 3 plus. That's another kind of component here. We have 3 reactions happening. I just saw the other iron one. Why did I not write this down? This reaction here is going to be negative 0.77 volts. So we're having these kind of 3 reactions happen in concert here. As Kevin has noted, yes, we do typically see that in more acidic conditions this is more favorable, but pretty much in so about pH 9 it does stop because you have enough hydroxide to prevent this from happening, but it's not common that you see very basic temperatures in pHs in the outside world, right? We typically see more acidic things. We know rainwater is pHs of 5 or so. Acid rain goes down to 4 or even 3, and so we typically see more acidic things in the environment. So what happens here? As you have a chunk of iron, as soon as this thing can kind of come in contact with water, because you need water for the reaction, right? You've got O2 floating around up here, just in the air. As soon as you have water kind of interacting here, what's going to take place is your iron is going to become, let me just get rid of the ion there. That's going to become Fe2 plus here. As a result, so the iron, of course, if you want to have ions, they need to have a place to migrate to, right? So you have to have the aqueous environment for them to kind of work out here. We have the electrons from that. The 2 electrons can go into the oxygen, right? So iron, of course, is a conductive material, so it does have the ability to move electrons around. So those electrons will come in contact with some oxygen at the surface, and poof, as a result, we have these 2 reactions happening, and now we get angry brown rust happening here at the surface. So we've got this rusting happening as a result. And so we're going to see that kind of the combination of these 3 reactions is what's going to produce that rust. Overall, if we want to kind of look at what's happening here, as all this comes together, is we are making various iron oxides in various hydrate forms. So we do see that this is that ugly brown goop there. It's very brittle, and has kind of none of the properties that we want. This is accelerated by very acidic pH. It's also accelerated by slightly basic solution. Accelerated. Oh no, that's not right. Accelerated by slightly basic pH. and also accelerated by salts. The reason for these ones is that we have electrolytes around, and those electrolytes are going to be acting as a salt bridge essentially to make this kind of fix the circuit, right? Electronic circuit. So the electrolytes produced by are provided by salts. So if you go near the ocean, or if you go to a place that has snow in the winter and people put calcium chloride on the roads to melt the ice, having the presence of those ions contributes to rusting much more quickly. So just because things can be conducted a little bit more efficiently, so you're going to end up getting your rust faster there. So unfortunately, a lot of the stuff we do will end up corroding our iron. It's kind of the most common corrosion. We do have corrosion of copper and other metals, but iron is the more kind of industrially important one. And so we have ways to protect it now. The kind of easiest way to protect it is by just painting it or putting some coating on the outside of it. That'll protect it from oxygen or water interacting with it. That'll protect the surface of your iron, and you'll be okay. If you paint it, you're good to go, except until the paint chips. Once the paint chips, then you have, yeah, we'll get to sacrificial anodes, yep. So once your paint chips, yeah. Once your paint chips, though, then you have surface area exposed to oxygen and potentially water, and then you get the rust. Sad times. But yes, there are other ways to do it as well. We can kind of have chemical protection. For example, if you coat your iron surface with zinc, the zinc is actually has a better potential for the oxidation than the iron does. We had the iron one written down here somewhere. That's going to be plus 0.44. I am writing this as oxidation potentials. Remember, that's just the reverse. So your reduction potential that's given to you on the table there, it's just the opposite for oxidation. And so this one actually has a potential of 0.76. So this is going to be more likely to happen. Remember, the more positive means it's more likely to be oxidized. So by coating it with zinc, you can preferentially oxidize the zinc instead of the iron. So O2 will oxidize the zinc instead of the iron, and so you'll be able to protect it. So this is technically actually going to be, since this is going to be an oxidation process, you will use zinc as what's called a sacrificial anode, which gives what's called cathodic protection. So we are going to protect our iron by giving it a sacrificial anode. So we are going to prevent the iron from interacting with the oxygen by throwing the zinc in there. What's also cool is because zinc is a metal, even if you chip your zinc coating, it will still protect your iron because it'll just form a circuit. Since it's a metal, it'll still conduct the electricity. It'll be able to kind of interact with the iron even if it's far away. So even if it chips, you'll still be able to have your iron protected by the zinc coating. There are other coatings that people use like chromium or nickel. as well to prevent uh, oxidation of the iron or steel. You'll also see magnesium is often used, so using iron pipes or steel pipes to carry water. Obviously, you're having iron interact with water. There will be dissolved oxygen in there that can lead to rust. All you have to do is attach a sacrificial anode with a wire to an iron pipe. So you've got your pipe going along. It's got your water in it as it goes. This is the iron pipe. If you just have a wire here connected to a source of some other metal that's more easily oxidized, like magnesium or zinc, you can have this protect your pipe as well. So this will be your kind of sacrifice here. That'll protect your iron pipe, so you can still use steel for piping as well. So steel is a great material, right? It's very hard, it's very durable, it's a good material to use, very strong. So unfortunately, it does come with that risk of corrosion. So you'll either coat it, make stainless steel using various alloys, or you can use sacrificial anodes to protect your steel in this manner as well. So of course, if you're using plastic pipes, this is not a concern, but we don't have to worry about that here. So you can use sacrificial anodes to protect against corrosion as well. So typically this is mostly dealing with iron because that's the biggest and most industrially important metal that is easily corroded. So that's why most of this kind of stuff is talking about iron corrosion. All right, any questions on the iron stuff here? All right, then the last kind of section we're going to talk about here is electrolysis. So these are electrolytic cells. Can you post? Yeah, of course, anytime. You can always do that. All right, with electrolytic cells, these are going to be non-spontaneous. Of course, non-spontaneous reactions that we're going to give. We're going to give them electricity. We're going to give them a voltage, and they're going to occur. So, for example, if we wanted this reaction to happen, we can just apply a voltage to it to get it to happen. So normally we know hydrogen and oxygen will combine to form water. We've seen that that's going to be the favorable, the spontaneous process. But if we apply a voltage to it, we can actually separate these two. So this is one way to get hydrogen. It's not very efficient because obviously you have to put electricity into it, but if we just take a look at we just looked at this overall earlier. What was the potential we got here? The potential is about 1.2 volts, right? So I guess it's going to be negative in this case because we're reversing it. So the E for this cell is negative 1.229 volts. So we just need to apply that voltage to get this to happen. So if we apply we can get this reaction to happen. it'll split back into the gases. So we can force it to go in reverse by applying an external voltage source. So we would either attach this to a battery or throw it into an electric circuit of some sort, and we can get this to happen. Another common thing to do with electrolytic cells is you can form other elements as well. So for example, if you have sodium chloride liquid, so you've melted your sodium chloride, you can apply a voltage, and what you'll get out is sodium metal and chlorine gas as a result. So you can forcibly separate ionic compounds by applying a voltage to them, and it'll work. If we want, we could calculate this potential, but it's not really necessary. The point is we can just force these things to happen. However, notice this can't be not aqueous, because the potential for this one is going to exceed that for water. So if we were to have this in aqueous solution and try to apply the voltage necessary, we're going to just end up hydrolyzing our water instead, not hydrolyzing, electrolyzing our water instead. And so as a result, if you want to kind of separate an ionic compound, typically you have to use it in the molten state that is anhydrous. So you don't have water being broken down. Instead, you want your ionic compound being broken down. So we can't use the aqueous version because this is greater than, actually I guess less than negative 1.229 volts. So because of that, if we were to do that, we would just have water being electrolyzed. Instead, we would not get our sodium and our chlorine out. So we can use this to kind of separate things like that. We can also use electrolysis to plate metals. So sometimes we want to plate a metal with another metal, either for aesthetic reasons, we like the color of it, or it's a corrosion protection idea. So if we have our zinc electrode here, we have some iron object, whatever we want to plate with the zinc. If we have this in a cell and we connect our iron object by a wire, here let's make it what kind of object shall we have? How about a star? We're going to plate this iron star with zinc. If we have this in solution, if we look at the reaction that's happening here, we're going to be oxidizing zinc, and we can then also oxidize or reduce the zinc ions in another location. So that's all we're going to be doing. Since these are just the opposite reaction, we of course would have no potential here. So just like with the concentration cells, we don't have any potential, but we saw concentration cells can give a little bit of potential. All we have to do is apply an extremely small voltage to get this to happen. Just a tiny voltage to this, it'll happen. So as long as we can, we have a supply of zinc ions, so if we have a zinc solution and we have zinc metal, we can attach another object, apply a small voltage, and it will plate the object in zinc. We can do this with other things. We can do it with nickel, we can do it with chromium, we can do it with all sorts of different metals, just by applying a small voltage we can force that metal to plate itself to reduce back to its elemental state on top of the object of interest. And so as long as we have our electronics set up so that we have electrons going this way through the cell, we're going to be able to reduce our zinc ions at that other electrode at the iron object and plate it. And so we will now have our coating of zinc on the outside. And that coating will be uniform, and it'll be thin, and it'll be everything we look for corrosion protection. So, hooray. So we can plate things this way. If we want to plate stuff, electroplating, say if we wanted to add a certain mass of zinc onto our object, if we've calculated surface area, we know how much zinc we want to plate onto it. We're going to see that the current, I don't know how to spell coulombs. We know that the electrical current is coulombs per second. Coulombs is a unit of charge. Current is, I guess I can't define it without using charge in it. It's the charge per second, right? It's the movement of charge. Second, of course, being time. Remember that 1 mole of electrons has 96,485 coulombs. That's Faraday's constant, remember? And so we can see how many electrons we're going to need stoichiometrically to plate a certain amount after we apply a certain current to it. So if we want to think about it this way, we can have our charge is going to be equal to the current times time. If we do that, that's coulombs equals amperes times seconds. So charge, current, time, coulombs, amperes, that's current, and then seconds. We can see how much. So let's go ahead and see this in action here. So if we apply, I don't know, 3.6 amps to an item for, I don't know, 3 hours. Let's see how much zinc we can plate with that. By using this. So remember, we're going to be able to go from coulombs to moles of electrons. We can go from moles of electrons to moles of zinc, right? Just using the reaction coefficients. So if we have our reduction happening, we can go from amperes to coulombs to moles of electrons to moles of zinc. And then I guess grams of zinc, since that's what I asked for. So it's just unit conversion as always. So we're going to see that the coulombs here, the charge, is going to be equal to the current times time. We have 3.6 amperes times, I guess, 3 hours. So we need to convert our hours into seconds. doing this, we get a total charge of, oh gosh, I have to actually calculate. I thought I had a calculator here. Oh, back to Google. Alrighty, 3.6 times 3 times 3600. Okay, so we have 38,880 coulombs. And so now we can take this, so we take our 33,880 coulombs. We have 96,485 coulombs for 1 mole of electrons. That's the charge of 1 mole of electrons. We have, in this reaction, we have 2 moles of electrons here for 1 mole of zinc. Computer, what's zinc's atomic mass?
Zinc's atomic mass is 65.38 unified atomic mass units.
Okay. And then we'll get our, that's the best use for Alexa, by the way. So, okay, so we need to multiply this by 65.38 divided by 96.45 divided by 2. And overall, we will end up plating our metal with 13 actually guess 13 because that's the sig figs that we have. 13 grams of zinc is how much we will end up plating. Yeah, 13.17, but with rounding, we'll get 13. Hooray! So with this, we can quantify how much we can plate. If we wanted to, we can do all sorts of fun kind of computations with this, but it's essentially the same thing. So you just need to kind of incorporate this idea of the Faraday's constant and then the ampere times time idea. So with that, you can quantify all sorts of electrolytic fun. So you'll have just a few homework problems on that in there. And with that, we're done with electrochemistry. Hooray! Hooray. So we can, any questions on that one, by the way? Hopefully nothing too crazy here, so only 2 new things with this, otherwise it's just plain stoichiometry, unit conversion as always, our favorite thing. Alright, if there is nothing, we have an easy chapter next. Well, it's easy in that it's not difficult. It's a lot of stuff we've seen before, but it is varied. There's a lot of things kind of happening because we're looking at just kind of reviewing groups of elements. So, all right, if there is nothing else, we'll start our next little bit here. We have a few minutes. We can start on hydrogen. So, we are skipping chapter 21 for now. That's going to be my gift to you at the end of the semester because nuclear chemistry is the easiest of the chemistries. So we will save that to the end to make your last bit a little easier. We will come back to it later. So we are now on to chapter 22, which is on nonmetals. So kind of if we look at what we've studied so far in general chemistry, we've looked at quite a bit, right? We've talked about so many things with different kind of compounds reacting together. We've looked at delta H, delta G, delta S, all sorts of things we've looked at, mostly looking at compounds. And we haven't really looked at elements specifically yet. So we're going to see that the alkali metals, alkaline earth metals are boring. Nobody cares about them because they do one thing, they give up their electrons and they're done. They don't really have any kind of extra stuff. But we see that we have the nonmetals and the transition metals, which are going to be our next two chapters. Will have kind of a lot more that they can do. And so we're going to kind of look at each group of nonmetals in this next chapter. And then in the chapter after that, we're going to look at transition metals. And so we're kind of just going to look at the elements now themselves. And then we're going to come back and finish off with nuclear chemistry at the end. So with that, we're going to kind of just take a look at nonmetals group by group. The first one we're going to look at is hydrogen, which is kind of a very interesting nonmetal because it's unique in quite a few ways. So we typically will put hydrogen up here at the top of the periodic table, right? We typically throw it there. Some people, though I have never seen this, some people put hydrogen here on top of the halides, but I don't like that. I like hydrogen over there, but it's definitely not an alkaline metal. It is not an alkaline metal by any means. We can tell this, first off, it's not a metal, it's a gas, right? So it doesn't have any metallic bonding. We see that it normally will form covalent bonds preferentially. It does definitely form ions, but it will typically form covalent bonds. And so it's definitely not an alkaline metal. However, it's also not a halogen either. So we might think, okay, well, the halogens always occur as diatomic, and we have all these other kind of properties with them. However, okay, well, let's write these kind of things out here. So hydrogen, it's not metallic. And relatively speaking, it has a relatively high ionization energy. Relatively speaking. So compared to all the other alkali metals, it's way, way higher. We would expect ionization energy to be much lower if it were an alkali metal. We also know it's not a halogen because even though it is diatomic, we see that it is a relatively high electron affinity and a low electronegativity. So, I'm sorry, electron affinity we always put as negative, so I guess we should say it's a low electron affinity. I want to say high because it's, in terms of negative, whatever, we'll just put it as low for now. And then it has a very low electronegativity comparatively speaking. So it's not really a halogen either. Plus, it prefers to be H plus over H minus. It can form H minus, but very often it's H plus that it tends to form. So unlike the halogens. So it doesn't really have characteristics for either one. It's not really an alkaline metal, it's not a halogen, it's kind of its own group. So hydrogen doesn't have a special group. So we're going to see that we're going to talk about many other, in this chapter, we're going to talk about groups of things. We're going to talk about halogens. We're going to talk about group 6 elements. But hydrogen kind of gets its own thing because it doesn't really have a group, because it's not really fitting in to its closest neighbors. So let's talk about what hydrogen can do. So hydrogen is produced by a couple of reactions. So we saw that we can make hydrogen from electrolysis of water. we can make it from taking a metal such as zinc and reacting it with an acid. But these are kind of small scale. So, like, if we were to do a laboratory experiment for us, if we needed hydrogen for a reaction, we would probably take some zinc and hydrochloric acid or some other active metal and throw it with an acid. We'd get hydrogen gas out. Or if we wanted to, we could electrolyze it. Either way, that would work. But those are kind of small scale processes, so they're not really efficient enough for industrial purposes. So what happens typically is they'll take methane plus water. They'll make hydrogen plus carbon monoxide. And this happens at, I think, I don't know, what was it, 1200 Celsius or something? Some high temperature that this has to happen at. And this is kind of the most, um, this is the kind of more common way to produce hydrogen in the industry. We use hydrogen quite a bit. Does anybody have any idea what the most common use of hydrogen is? Hydrogen gas? I'll give you a hint. It's our absolutely favorite reaction that we've studied 20,000 times. It's this one. Yes, the Haber process. Yes. This is the most common use for hydrogen gas. So, by far. Yeah, they'd probably combust the CO or do other things with it. So, carbon monoxide is actually pretty useful for uh, for for various chemistries. So, we're going to see in transition metal chemistry, we're going to see carbon monoxide a lot. Um, so they can either isolate it or continue its combustion. Yeah. So if they want to keep it and use it for something, they can, or they can continue combusting it for sure. Though obviously they have to separate it out first because they don't want the hydrogen to combust, because otherwise then we just get the water back again, and then there was no point. So yeah, they would separate it and then do other things. Um, so the most common use for hydrogen is for the Haber process for making ammonia. So, because ammonia for fertilizing purposes, very, very important. So, it's for agriculture overall. So, there's other things that we can kind of do with hydrogen here. Um, Chemically speaking, we use hydrogen for we use it for reduction of organic compounds. Perhaps most I don't want to say unfortunately, but we can make unsaturated fats. We can make them into either saturated fats or into trans fats. So in not only in just kind of chemical industry, but in terms of production of foodstuffs, we can hydrogenate fats. You've probably, you can see partially hydrogenated soybean oil or whatever on your labels sometimes. That's say trans fat. So it's something we typically want to avoid, but that is something that it is used for. So it's another use for it. So unsaturated fats are liquids, saturated fats are solid, trans fats are solids. They're spreadable. So for kind of convenience, having it as a solid can be useful. So we're going to see that uh, that's kind of one way they'll use it. So it's another way there. So let's see. We can also take. What else do we use hydrogen for? Typically, though, you do need a catalyst for this. By the way, typically, usually that's palladium. So you'll see that in OChem, when we do OChem, when we talk about reduction using hydrogen gas, we're going to see palladium on carbon as a very common way to do it. There's also other ways to force it to form certain products. Um, let's see, what else do we use hydrogen for? Of course, we know that we can form H plus with various, uh, what are they called, polyatomic anions. Or halides, and they'll form acids. We can see that if we have H minus, those are going to be with more of our active metals. Those H minus is a very strong base. It's actually one of the best bases for use because if we were to put a hydride in water, we would end up getting our hydroxide ion out, but we get hydrogen gas, which immediately bubbles out and leaves the reaction, and therefore Le Chatelier's forces the reaction to go to the right. So it's a very, very efficient base because it forms a gaseous product that just bubbles out of solution. Out it goes. As a result, equilibrium is pushed to the right. You force this reaction to go. It's also extremely exothermic. So it's a very favorable reaction to get rid of this. So hydride is a kind of crazy little, tiny little super base. So you'll see that things like KH or sodium hydride, these are very good, very strong bases. Or calcium hydride also. And so they'll react very strongly with water to produce hydroxide, leaving it in a basic solution. So, cool. We've already talked about acids quite enough. I'm sure you guys are done with talking about acids. So, we're good there. H also forms relatively strong covalent bonds with other elements. Notably, carbon-hydrogen bond is very, very strong. We're going to see that other elements with hydrogen, we'll see ammonia is a common one, water is a common one. These are relatively strong covalent bonds. The water one less so because it can be a little bit acidic. And so these are kind of very important biological bonds that we have. We know that hydrogen bonded to nitrogen, oxygen, or fluorine will give hydrogen bonds, which were a strong intermolecular force. So as you can see here, like kind of this chapter is just going to be a lot of kind of review and general information. I have no idea what I'm going to ask you on your exam for this yet. I'll think about that. Oh, we're already out of time. So I'll give you some practice on that. It'll probably be similar to the homework for this chapter. So cool. We'll continue on with this hydrogen stuff tomorrow. We have then I think we're going to talk about halogens, oxygen, carbon, silicon, all these fun other elements. So we'll talk about them tomorrow. So we'll see you guys then. You have enough now to finish your electrochemistry homework that'll be due Saturday. So don't forget your exam is next Monday. So we want homework to be due Saturday. So make sure you're working on that so you don't get kind of stuck towards the end there. So with that, we'll see you tomorrow. And then tomorrow I'll post this homework so you guys can start looking at that as well. But focus on electrochem right now, and then we'll get this going. So, all right. See you guys tomorrow.